Oh, no. All right. On to you. Oh, and is there a way to see who's on the show? You don't know that's I should have asked before we go.
We can, that I don't know, I think we could go.
So we just have me just stare to one side.
Yeah, I don't know for sure.
I can. Or you know, there, the top right button.
The top.
That's just like a little chat box.
Yeah.
After that, I'll stop on the computer. Right. Okay. List all of the group chat. This laptop is unfortunately awful, so I can't really join the call.
I can try to look here.
Alright. Okay, I guess I'll try. This computer doesn't have. Oh, cool! It's like live embedded in it. A little side.
Wow.
Let's see if my computer crashes. No, this is
That's
well installed or something. It's all.
That's a nice tiny computer. I like
It's cheap and
computers.
it shows. It's the fact that YouTube link that up. Slowly. Thing. So here's a chat window. It says, "I'm concerned about your privacy." Live chat. I don't see your message.
I'm gonna say, yeah, I don't see it either. Maybe it's live, so it gets lost.
Or I catch up. And then the video thing is a bit better. And of course, all this is going to be posted on YouTube, so we're going to spend the first 10 minutes of me just like, how was you? Oh, so it's 7 now. We'll give people a few more minutes to show up. Oh, I see. You've just posted something on YouTube, or Prashant just posted something on the chat saying, hello, this is you. Oh, thank you.
It's not there.
You know, I think I can leave this open, and so people can already.
Oh, yeah.
On my personal YouTube account. So I will be able to see, or will I, because players not actually coding. Do you think, yeah, could we open the link there, or is that going to be on those feedbacks?
I'm sorry. Wait.
Yeah, I think what you're doing is something I would support. Can you open up this video in YouTube on my computer? So
Yes.
I'm just.
Oh, yeah, that's.
Because if people, no, feedback. Really? Okay, I think that might. Yeah, so I can't see anything in the turbolizer. Yeah, but so in this way I can look over and see if there's more chat. Hopefully. Yeah. Okay. And it's not going to try to do anything smart. It's like, oh, the chest is like, it's muted or something.
Yeah.
Sure, this way to do all interactivity. So. future. Are you all?
Because at the end, it will be, yeah, I'm ready.
All right, ready for a raise. How do you feel about a raise? This is Aaron's talk show. We're here against the speaker.
I feel like I understand them better since from the time that I realized that they are continuous space in memory, and since I understood like why pointer arithmetic actually works, that was like a really moment.
The language you're most familiar with is JavaScript.
JavaScript, yes.
Do they have functions in JavaScript?
No, but I had a taste of C in the for a month, and then I saw pointers, and then it just clicked.
Yeah.
Yeah, so that, and recently I was trying to implement, this is a cracking the code interview question where you are asked to implement 3 stacks with 1 array. I got close, but I did have to look at the hints, and at the end I ended up looking at the solution, but I still this is a presentation.
Oh, so it's still has the stop project, so I assume it's like they remove the
Yes,
sorry, I'm next directing.
that's fine. So yes, there was cracking the code interview. I actually haven't finished the question because the question suggests, what if the array, you think of the array as wrap around array where it's kind of circular, and if you push, you will just keep going, erasing or overriding other elements. Yeah, so I'm like implementing that currently, like a wrap around array where
This is a part of the 3-step.
yes, this is actually a part of the 3 stacks. And this array does have a fixed length. Not well in JavaScript we have like dynamic arrays are the norm. So yes, I've been exploring more arrays in that way. Yeah, this is actually the first time that I thinking of an array as a circular data structure. Or like simulating that kind of behavior.
I'm curious, you had said, oh, you didn't really get arrays, but like, you didn't get, I guess, the motivation for arrays.
Yeah.
So, do you remember kind of how you thought of them before? Because I imagine that's what a lot of people are. What was that bridge? Because that's what I want to try to build.
I think I
remember that
remember.
hard question. So.
That is a great question. How did I think of them before?
How did you get
It was more like trust. I was just trusting what the instructor will say about arrays. Yeah, so I guess I don't have any rules. I was kind of trusting of the facts that were mentioned, but I didn't kind of realize it for myself or fully understand.
And so I guess when you started learning C, you saw kind of how it worked.
Yeah.
And then, oh, here's how you get it, the closest thing to a collection. You just sort of you saw that and said, oh, this is why we care about arrays, because they come up in C. Like, is it that, oh, they come up in C, and therefore we need to know for C? Or like,
It was like I guess I didn't realize the fact, even though I heard of the fact that an array is a contiguous space in memory. I didn't. I guess I didn't fully understand that until I actually saw that the address of element 0 is exactly that many bytes as the address at index 0 is that many bytes apart of the item at index 1, where that amount part is the size of the element is contained. And that also make clicking the fact that we in C you care about data types, like saying this is an integer, this is a character.
That's true.
Because what you need to know, for instance, for knowing how much memory you need for an array to contain a word.
Yes. A word.
Or
what course were you taking? That's like from days.
oh well, not the word in the computer science, meaning the string.
Oh, fine. Okay.
I am aware of that, but I'm not sure exactly.
And being in front, so I won't be wrong. I'm pretty sure that's 2 bytes.
Oh,
Byte word, the double word is 4 bytes. Something, but like it's still used today.
Cool.
Today, people usually think about college short. Sort of.
Okay. Yeah, so I think I'm fairly comfortable with arrays. I haven't done.
Just so you know, if you want to show me 5 minutes, we'll just, you'll be the special guest on my radio show.
I feel flattered.
You heard it. Okay.
So I guess maybe I might get stumble on multidimensional arrays. That one is, I realize I do not have much experience in that. On matrices.
Yeah. I didn't prepare any questions for that.
Okay. Yeah, I guess that was is the next level of arrays, I would say. Or, yeah, so like thinking of that, what else?
Have you had any array engineering questions in practice, or like in engineering?
I cannot remember one interesting one actually.
Oh man.
No, I saw when I was seeing some C code, there was this problem where you had a matrix, and like a constant plan, right? But you had to, the matrix will have zeros and ones, and zeros mean the empty space, and ones mean obstacles. And you had to build the biggest square.
Square for a region.
I think, well, yeah, region.
Yeah, sorry.
And yeah, I remember I couldn't solve it. And I do remember thinking that maybe dynamic programming could help in that case, but that's just a speculation.
So I'm always interested for hearing about questions in practice. So thank you for questions. Because I think, when I, looking at the code, for instance, other resources, it's for very, they try to have questions for every possible audience, experienced people, junior people, everything between. So kind of, and I don't really know how to distinguish, or I don't know how people distinguish them, so kind of knowing what pursuit. Graduates, is that what you're?
Oh, yeah, alumni is a more common.
Alumni actually encounter. And also, there's questions where it's like, oh, here's very C-centric questions, and then you know about C. But most of you are distinct. So it's like, all right, I probably shouldn't focus on those questions, but I don't really know. Yeah.
And I've been curious as to, I guess, how in JavaScript you can have a mixed array where element at index 1 is a number and element at index 2 is another array, yeah, any other. Yeah, like, I guess that's like, I was thinking that maybe it's an array of pointers, then each one is pointing to a different thing, but I guess that kind of, I know that in C you have to specify where the pointer is pointing to and the size of that or the data type of that. So I don't know if you could have an array of pointers where each pointer is pointing to a different type. But yeah, I guess that's like an implementation.
Your integration is very spot on whatsoever. That is, so I guess I have not implemented JavaScript interpreting, so I can't really look, but yeah, like that's C. It's funny how you were saying that C is sort of strictly typed in some ways, but actually, like, other people would, or other languages are much more strictly typed. C can actually be very free in a lot of ways. And what, do you know what a union is? But yeah, right, C, there's a convention where you encounter, where there's a cargo, you encounter the type void.
Yes.
Okay. So by convention, you have a pointer to void. Which, like, what does that mean? You have a pointer to something that's not really a type. And that's sort of the thing that says, I promise you I'm pointing to memory, but I'm not going to tell you what type it is. And you know about type casting?
Yes.
Okay, so then you can cast that to whatever you like. Then you can imagine you have maybe void pointer. So you have your array, and each element is a void pointer, and then say, and do you know what an enumeration is?
No.
Okay. It's integers, basically. Just it's a way of notating that integer 0 is recurring singles. So you might say integer 0 means 8, integer 1 means char, and so on. And so in that way, you know, just a pointer and an integer, but then you're starting to say, oh, hey, this is, the integer tells me what the pointer is actually pointing. And then you can start to cast it.
Oh, that's really interesting.
So that's roughly how, and back to your other question about 2-year array. I can, like, analogy I always like is a lot of these questions and stuff, they try to help everyone build a vocabulary. I'm like, there's just a million tricks, sounds too disparaging, but just there's like a million ways we think about the data and how we, and so I can talk about what I think the right vocabulary is to address that question. Like, I can just jump in at this point.
Yes.
If you want to just keep on chatting, we're good.
I wanted to mention that something like, I guess, like I was kind of go without saying is array sorting. Array sorting an array of integers. I'm not sure if we're gonna look into that here, but
just how it is done.
Yeah, well, like all the algorithms that are for doing that, and like I don't know how to implement bubble sort, which is the most inefficient one, or one is the most inefficient.
Is some funny feature. Sure. Okay, so we can be a bit more frequent today, especially. Yes, I'm sorry, because I know another Jay had mentioned that he was interested, longer had mentioned he was interested in sort of a more like traditional lecture, for lack of a better term, of like, here's just sorting algorithms. I'm not sure if other people, like, I guess this is going back to pedagogical questions, of like, should be very, like, here are questions from a website that you can program, or like, here's your conceptual stuff. So it's still, I'm happy to do whatever. I have my own opinions on what to do, but this one,
I feel like sorting an array for me has been like learning the code for doing it rather than intuitively know it. I don't know if you know what I mean.
Okay, you want to see how it actually goes.
Yeah, it's like I don't want to have to remember how to write bubble sort, but kind of bubble sort be developed as I go.
not bubble sort. Selection sort is just for insertion sort. I heard this. To be honest, those are, I think, more intuitive as well. Like, as in, if I give you, shuffle deck of cards and you say sort, you might do something like selection or insertion. You wouldn't really know this.
Okay.
So, no, this is sort of like, so why it's easy to analyze. So,
that's true.
because it's so.
That's a good point because I guess I have been having a hard time trying to understand bubble sort, but it's not intuitive. It's not the way that a human most likely will do it.
Well, in sort, I always get it mixed up, but like both of those are sort of more efficient, basically. Not as intelligent, but it's not. And now it's like, oh, I have to make corrections there. So if you'd like, we can start going through this.
Yes, absolutely.
Speaking of posterity, archive forever, and then machine learning will start. How did humans communicate back then? Alright, so that sort of was riffing off of this anyways. So you already sort of have your own, like you leave the raised hand. So if you'd like, you can just dive right into the questions. And the answer is always no, but did you have a chance to look at the it's a lot to ask, just sort of say like, especially I try to get it up before the weekend. And it doesn't happen. We're live on television. So yeah, we're just about to dive into questions. I think someone wants to. Yes, this is. I just had a talk on security. How you keep one door open and people use it so to jump into the first question, we have removed duplicates, and as it is asked, so sorry, I also didn't have time to translate it to Python, so we're doing it in C-ish. I'm going to try to be a little free with. Oh yeah, you're familiar with C. You're familiar with Java. The syntax shouldn't be crazy. I'm familiar with C. So, oh yeah. You told me that before. Sorry. Yeah, move duplicates, and we have. Okay, so here it's a vector, but this is basically an array list. Yeah. I'm just trying to be faithful to the website. None is sorted. None is sorted. Change numbers so that yeah, okay, so we'll put that there. So the question as it is asked says, given a sorted array of none, remove the duplicates in place such that each element appears only once. Return the new one. So let's just remove dupes in place and return the new length. So that's our charge. So first, in place, what does that, is that something you heard before?
Yes.
Okay, so.
I think it means don't create another copy of the array, just try to not allocate any other memory.
Yeah. So there are some languages, but if I were to give you, here's a formal question. So if there's some function foo and it takes, an object, so JavaScript, I guess you can leave out an object, and you have field equals x, for instance. And so you can imagine this is also the case. We're doing something to Java, and then we call bar, or we have a function bar, and we have object b. And we have b dot field equals equals y, and then we call foo of b, and then we print b dot field. What will this print?
I think it will print.
The real answer is a very high language. So like this is more of getting us all oriented together. So here we have foo, and it takes an object, the parameter, and it changes the field to field. Sets it as. And just to make it explicit, I said, okay, foo bar calls foo. It calls it b, and previous to that, it sets the field to be the y. So all right, there's two options, right? It's either going to be x or y. What if it's seven?
I think it was going to print X.
Yes, I would guess in Java, I'm not an expert, I would guess in Java script, it would do that. And I think also in Java, it would induce that when you pass an object, it's sort of, so this, generally we call this passing by reference. Is that a familiar term? Yeah. Okay, and like I know in Java, if you pass an int, this, and you increment the int here or something, it won't be visible outside the call. I think. I mean, a little odd.
I know that in JavaScript primitives are passed by value.
Yeah, so it's usually it's passed by value or passed by reference. There's also more exotic ones, but let's not disturb. Those are the two that will actually come from. So in any case, that was all to say that in C, there isn't passing by reference. Or you have to explicitly pass things by reference. And what you do, that's what the ampersand is. And in any case, so that's just in case you're wondering. But the point is that when we talk about the phrase in place, it basically means you're given the thing, and let's change that thing. Like the goal, like it'd be sort of silly in a sense if we have a function called remove duplicates, and it takes numbers, and it removes the duplicates from those, but then doesn't give you a result. So here we're returning an integer, and sort of implicitly this is also kind of something we're returning. Like we take it in, we change it again. So that's the motivation for in. So that's why we means in place, that's kind of why it matters. It's our input. In place is just
definitely more clear now.
Yeah, and then so just the later point, the rest of the question says, do not allocate extra space for another array. You must do this by modifying the array. That's with constant extra memory. And then kind of in roundabout way, it says it doesn't matter what you leave kind of at the rest of the array. Like it only has to do it to link. So what are our thoughts about this question? And it's very open-ended. When you say directly, you mean like the list? It's like an array list. An array list.
Like I'm thinking about, would we just remove, by removing the duplicates, do we want to put an empty value once we see a duplicate, or should we move once we remove the duplicates, should we have the array with no empty spaces in between elements, basically, since we remove the duplicates?
So let's talk about some test input. And I'm trying to facilitate more interaction. So here's kind of the first interesting thing. So just make sure what's the length of this array? 2. Okay. And I'm just trying because so how would you think, or well, this is almost too simple for that question. So you're saying, for instance, if we have 1, 1, 2, 2. Let's get oriented. What do you think the output should look like?
I think the output should be something like 1, nothing, 2, nothing. So there's plenty I.
Yeah. So another fun fact. sometimes in the hash tables, we might have tombstone values where like, this isn't really here, or like null or something. So I mean, now you're slowly pulling more information up. In some contexts, that makes sense. For this question, I would instead ask that we do this. And then sort of, we can have whatever we like. Because there's only 2 unique values and we only care. Like, if you want, you can put 7 and 8 here. Like, we probably won't bother, but like the point is that we don't care what's left. So we could have some steps and not that. What we want. But we kind of want to push everything towards the front. And the way to build some intuition to that, you can imagine that, okay, we have this vector of elements and we want to, we basically want a smaller vector, or sorry, array. We have an array of elements, we want a smaller array, where it's just the duplicates are removed. And to kind of think about that array, it'd be better if it was all front. But we don't want intermediate values, we just want to pretend as if it were the new length. This is just a help building intuition of like kind of. Not that you'll see exactly this question, but if you see something similar, these are handles. Start to think about some of the implicit assumption in the question.
I guess I'm curious as to see if an advantage of putting them all at one end will be that we could reuse the space that is not used. That's still part of the array. Is that something that would be possible?
And the motivation that I know about this is really more about how allocating an array, or allocating an array is expensive in some contexts. Day to day, if you're doing anything times, sorry. And so it's more like we had, an actual motivation from this that I had done before, confidentially, was, if you want to find all the users who logged in, you have like, let's say you have a collection of machines, and you have a bunch of users, and you want to know who's logged into which machines. Just which machines are using what's. So you'll have redundant people on each computer, but you want to just know who's used any machine recently. What you do is get them all together, and so you're going to get a list of some duplicates. Where was I going to go? But then at the end, the only thing you care about is, here are the users that use the machines. So, and if you're doing, and it's, so like that you have kind of extra memory, and whoops, that's what happened. It's more like, hey, I know that's what I want ultimately. I could make a new array and copy the unique ones into it. Well, obviously sometimes there are where maybe you want to do something else with this array, so you do actually want to don't even keep the one with the new ones. Yeah. So do we feel sufficiently motivated about this question? I know it's a self-deleting question. Oops, I can okay. So let's go by hand. Yeah, let's just.
Well, we use vector because that's part of C, right? That's one.
Yeah, sorry. That's
Like, why do I'm still keep going back to vector.
Yeah, all right. No, it's fine. Really, you've done this. It was a digit. So here's an info. That's more or less. And C, the array syntax go here.
No, just the word vector.
Yeah, it's not. People are not in universal agreement that that's the right name for it. It's sort of like allocation. So, so before jumping into code, so now we understand inputs. If we have input like 1, 1, 2, 3, 3, we want a result that looks like 1, 2, 3, hopefully comes. And then, I put question marks just in the sense that we don't. And we want to return 3. That's the length of it. So, how might we do this? We can do this by hand. So we have a whiteboard. I invite you to do that, or you can brainstorm for.
Yeah, that's something to do. But, yeah, so just draw it, don't start writing anything.
I mean, if inspiration strikes and you want to go for it, I'm trying to be a little bit more like, all right, let's solve the problem more.
What I'm thinking, I'm just gonna go, I'm not gonna think about code. I am thinking about code, but I'm not gonna write any code. What I'm thinking is, I think I brought this up last week too. And it's only because I know this specific data structure doesn't allow for duplicates. I want to use a set. So I want to say basically with the set, it doesn't allow for duplicates. If we do like, let's see, this, I'm sorry, this happened. It's whatever, this is not what you call it, I'm just writing it. We'll do a set first, and then we'll do, because it's an array list, we'll do like a for each. So we'll do for each integer inside of the array list, and we'll check it to see if it already exists inside of the set. And if, of course, the set is not going to take it unless if it does exist, but we'll check to see if it contains it. So if one is already in the set, like right here, and we say, hey, is one there? Yeah, it's there. Cool. Is one there? Yeah, it's there. It's going to automatically reject it because that's the nature of it. Then say we get two, we say, hey, is two there? Add two to it. I think add is there. But you said remove. So it will automatically remove because it won't allow for duplicates to go inside. But I think sets have a remove function if you want to do it that way. Say you wanted to pass it to another data structure. But I was just thinking about a set because I know it doesn't allow for duplicates.
Yeah, so that's a set is a good vocabulary thing. Like it is a very useful tool.
Okay. And then we will do like for each. And again, we're going for each. And then if we do come across something that doesn't exist, I believe, because set extends from linked list, I believe there is an add function.
Yeah, so I think I like that you've identified like, hey, a set, if I can editorialize it, like we can just go through the whole array and dump it all into the set and trust that if we insert something multiple times, it's gonna, yeah, like you were saying. And so like, certainly you often want to use sets to say, hey, do you have this or do you not? We can even be sort of simpler here, just put it in the set, and then we get that sort of unique behavior. You know, kind of pretty immediate.
Straight to it, but that's just a thing of alternative outside of the set. I guess we could, this might be a little slower, but you can use like a for loop and you can check the value at index. It'll be a nested for loop where you're checking the value of index I with the value of index j plus 1 to check to see if they're the same. No, but that won't work because what if one is here and two is here? It's going to say these two are the same. Yeah, that's not going to work.
So like, you know, like, look, we are promised that the array is sorted. So I think that addresses the concern for just,
Okay.
because I do like the for loop better.
Oh yeah, so you did say it.
It's common, but yeah. So I think I think I see what you're saying. Using it for
I think it might have to double check with the set versus the for loop. I think the for loop will run for n squared.
I think we could definitely take advantage of the fact that it's sorted so that we can only go one, but we only need to go once. Where we could maybe start instead of just starting at element 0, index 0, you will start at index 1.
And then just check zero
backwards.
Yeah, and then we probably don't even need the second loop because we just check.
Yeah.
Yeah. That will get rid of it.
Check backwards.
So then it could be over 1. And then we just want to display it, so we can do a system out or a log, console log.
Well, the API that we're asked to do is to actually change the original array that we have. So that's what I meant, or that's what question in place. So so if there were ultimately here, there were three, like we want to take the input array that looks like this, and really like explicitly change it to look something like this, and then return three. That's our API. When you're actually doing this for debugging, it might be good to have lots of console log there in terms of what we want to deliver.
We're only returning the length. I guess because we've modified it in place, we already have it, we don't need to return the array.
Yeah, syntax here means, I know this is not JavaScript. So first thing we also for coming forward. Well, that's always fun, and yeah, so if I editorialize a little bit, and then I want you guys to continue exploring the forward thing. I think it's very good. Just to follow through on step one. So I want to, if you're like, oh, we have a vocabulary almost, I just want to try that on its all basis. Then rewrite it a little bit more specific. Then you can language, you could have like, a set S, that's a semicolon. And then like, for int I equals 0, I is this thing. Nuns dot size plus I S dot add nuns I nuns sub I. And then how would, so this gets happen. We need to modify the array because we're supposed to modify it in this case.
But how, wouldn't we be breaking the second rule, which is remove duplicates in place? Oh, I guess not. Well, because I'm thinking, oh, we're allocating memory. That will.
Yeah, so this is not going, so the punchline is that the sets approach is not as efficient as something else that the for loops gave away the game. Just to follow through with this. Or X and S. Sorry. I mean, depending on how one another index I, that you sort of follow along there, and switching languages, right? And then you just do nuns I plus equals X. Or S dot something. I mean, sort of just went ahead and barreled through the answer. But this answer, because I feel this vocabulary pretty good. And I think you've seen all these pieces before. This is kind of still out. So here, oh, S is now. S is. Here, S now contains all unique elements, or it has one of each element in our original input. And so, kind of skipping ahead, hey, that is the return values that we want to give. Like the length of the sub-array that has only the unique elements should be the same as the size of the set of all of them. Do you see that sort of relationship?
Yeah.
Just, it's not super profound, but it's another nice little trick, And then, depending on language, sets could or could not be sorted. So here I'm cheating and saying, let's assume that if we go through the elements of S, we will go through in sorted order. But then we just copy it back out into numbers. So that's a very.
Wait, you said we just copy it back out. So
Oh, sorry. So great, we now know the length that we need to return, but we still want to modify our input array. We want to write back into our input array the unique elements in the sorted order.
you know, because the sort of motivation is we're shrinking the array we still have. And so there's just some syntax to do that. And so I guess what I'm saying is, oh, here's how to kind of follow through with that initial, or one way of following through with that initial idea. If you're in a set and how you know, you can get all you need done with that. Right? But we can do that. And you guys were already sort of talking about how to do that. So now that I've distracted you with this wrong, or with this inefficient approach, I'm erasing this. I guess it's forever, it's immortalized.
With the efficiency of this algorithm being the implementation of the set, like the insertion time, maybe.
If, for instance, nums had no repeated elements, and that's not the only case, that's just thinking here. How big would this set be?
As big as the nums array.
And sets are usually sort of more complicated than arrays anyways. But the point is, okay, we could potentially allocate a lot of memory. And we don't need to. So that's the extra challenge.
I see.
So you have another so to I think I was excited that you guys were talking about this already, or the for loop method. Do you think we can spell that out a bit more? That you guys can spell that out more? I'm trying to be sympathetic to the ecosystem.
Yeah, I think I would like to try.
All right. Well, so I might have a for this. We'll proceed.
So I think that we need to keep track of so we need to traverse the array or go over each element and keep track of kind of the current element that we're looking at and the element that we're comparing that element to. So, yes. So it is for that. Maybe we could have a variable, let's call it current element. Current. That is going to be equal to the num sub 0. So that we are looking at this element. Then I'm thinking let's start looping from the second one and see if that element is equal to the current element. In which case, what do we want to do in case that it is? Maybe we can just keep also the index itself, so we could copy it, so that if we see that it's the same, we just take note of that. Take note that this spot here is the same as the previous one, and then move on until we see something that is different. In this case, we see 2, and then because we took note of the index, we can move these 2 from here to that index. And then let's say we did that. So 2 overrides 1, and we were currently on 2. We override 1, and then we keep going. But we'll need to increase this this index that we have, like pointing at this element and move it to the next available spot. So that's kind of sounding very complicated.
Yeah, you're thinking like, because I'm not sure if we're on the same page, but you're thinking about reassigning the index values?
Yeah, reassigning the values that are at the index that we know have something repeated.
Because what I'm thinking is if we use, for example, what's on the board, 1, 1, if we're checking to see if at index 0 is, index 0 is what we're starting off with. So that's going to be I when we iterate. If I plus 1 and what's at I are the same, I think there's a remove method for an array, right? That remove, or is a way to take it out?
The one that I know of will remove at the end.
Remove at the
And
end, right?
there is one that removes in the middle, but that's like very inefficient
Mm.
because it has to remove everything else. Once.
Yeah, and then we'll have to copy the array over, and then to be able to do that, yeah, that's not gonna make sense.
So maybe it's not like, maybe we don't need to go looking back, but looking forward.
Okay. So
Like
yes,
we're starting here and we see the next element is the same.
do you
To just move.
do you wanna? This is like you said, instead of looking back, we look forward, right? So why don't? It's kind of weird and it's a little hacky, but why don't we just start from the end of the list and decrement down instead of iterating up? So we start from the last 3.
Okay.
And then the method that you know of where we could remove at the end, right?
Yes.
So we could remove, if there's a duplicate at the end, we remove it, and then we keep going, decrementing down. It's a little hacky, but
I see.
just so we don't have to worry about copying another array.
So you mean like, but we still need to know if it's duplicate to remove it.
Yeah,
So
of course, we have to double check. So we have to double check if array.length minus 1
this
is
one.
equal to array.length minus 2. Would that be minus 2? Minus 2.
Then remove this.
Then remove 1 if that's possible.
And then
It's hacky a little bit,
but then how do we move up to the next one? We were array at index array.length minus 1, but now we shrunk the array. So now this one is array at index array length minus
we
1.
still run into the problem where to make up, we have to reorganize the array and space.
Yeah, and once this one is no longer repeated, then the method will remove that.
Yeah.
And I'm not sure if the remove method will modify the original array or actually copy of it.
I said it was happy though. So hacky.
So I have the feeling that we will need to go with some reference to slots in the array to copy of it. I don't know how viable that will actually be. But in terms of
Go ahead.
yes,
Only a 3.
Sorry?
I said it's only a 3.
Yeah. Well, and the potential infinitude of the future, all of posterity. So, yeah, so the idea of, we can, hey, it's easy to remove from the end. That's definitely true. Or like, almost exactly kind of work that. You observe that, hey, APIs often remove elements from the end of the array. And the reason why they provide that is exactly because kind of what they're really doing is they're just decrementing some length counter. And which is sort of, that's just like, that's sort of the motivation of why, hey, we're removing all the duplicates and then we return the new length. That's sort of the same idea of just removing the last element and decrementing this or context now. So the idea of, let's exploit that sort of simplicity and go backwards, just as a simple way. Again, I've seen all these questions a million times, so it's probably others, but if we have like 1, 1, 1, 1, so a lot of duplicates, and then like 4, 5, 6, 7, 8, this will sort of put us in the position where like, if we call like dot remove at this index, we still have a lot of the array to slide back. So the idea of, so when you were talking about, let's kind of use the remove method, which is often available, it will take linear time, but what it will do is it will remove, this element, for instance, if you call it remove dot 1. That's remove 0, remove 1. It doesn't actually remove anything. What it will do is it will take the rest of the array and copy it down by 1. And then maybe decrementally. And so that approach, this is just to illustrate that, this will still take basically O of n for each time you call remove. So going from the back to the front, calling that move method will still be quadratic. But again, just from another direction. Like, isn't that sort of interesting that when we took that remove API is really remove that, the way it's implemented is it says, I want to get rid of this. I want to get rid of this element. Right? That's kind of what we want to do too. I'm going to slide down everything. And follow through with that idea here. 1, 1, 2, 3. So we run that current algorithm, which is a little slow in our head. What we do is we say, okay, start here. We see that we somehow see that this is a duplicate. So we remove it, and what we do is we copy these contents down. So we copied this last 3, it's still there. It's original's still there. Then we go here, we go here, and then we say, these 2 are duplicates. So it'll look at me.
I think you have one extra correct that you didn't have in the original.
Oh, sorry, I two incorrect. Yeah.
No, but then you have 2 3s in the
total. So this is the original array, right? Yes. And these 3 elements, I'm saying let's take all 3 of them and copy them. Offset by 1.
I see.
But because we're copying it, this is just to say, we're not going to actually change the memory involved in this array. So something will still be there. And because computers hopefully do what we tell them to do, it'll still be a 3, simply because we have it right. So then we see this, and we say, okay, this is a duplicate. Or this isn't a duplicate. Then this is a duplicate in the sense that it's the same as the one. But then, cross it out, and we copy the 3 to that, and then things get a little fuzzy near the end. We kind of still end up with an array that looks like 1, 2, 3, 3, but we also have some information sometimes saying that actually the only unique length is 3. So this isn't giving us the immediate answers that I hope. What you see is like, hey, when we have multiple duplicates in a row, we don't really do much. So maybe that's where some of the inefficiency can be kind of smoothed out. In the interest of time, should I just sort of dive ahead a little bit more?
Yeah.
And that's fine. So as always, I encourage you, even if you go to the whole exercise, go home and do it again, just because kind of going through the motions really does help kind of solidify everything. And to be fair, you guys are definitely I think just, at the time, you fill it out quick. So, now that I say that, let me make sure I I'm getting old, I'm forgetting all my old tricks. So, base cases, what's the simplest array we could get?
Empty.
Yeah, okay, so if it's empty, it was great. If empty, what do we return? Or what do we do with whether
If it's empty, what is this? We're returning an n. I guess we'll return 0.
we have a core?
Return 0.
Yeah, but if empty, there's nothing to, everything's unique, there's nothing bad.
I'm just saying that because you put it in as part of the method signature, so it has to return.
Yeah. And that's definitely if someone asks me this question in general, as it is phrased exactly here, we definitely always got to return something. It's in Java. JavaScript might be a little weird. And so, what's the next simplest array we can imagine?
1 element array.
Yeah. And do you think we have any duplicates in a 1 element array?
No, we're not.
Okay. So if length is 1, how many duplicates or how many elements are in the array that we're done with? Yeah. I should have started. Yeah, I do want to strip it. Oh, I want to get to all the fun stuff. But like really spending a few minutes of thinking of the simplest examples of the simplest test templates that can really help just kind of also give you an example of like, I would approach from. So those are the base cases. We wrote those down. Can save the space on erasing them. Yeah, I probably did okay. So a few things I'll observe. So okay, now we're dealing with an array that has like some interesting length. That's 2 or more elements. And from the perspective of, okay, let's kind of slide things down to get rid of the duplicates. Well, the first element is always unique, just in the sense that there's nothing before it that could be equal to it because there's nothing before. That's just kind of a way of thinking about this question. So I'd say so I would start some counter in C1, and then I would look at all of the following elements. So for int I equals 1. All right, I probably could have done this here. Sorry. I is less than nums size, so this is pretty boring looking for I So the only interesting element, this isn't 0, this is 1. So we're looking at the second element in the first iteration, just because we kind of are. You don't need to do it this way. And so we were really getting there. You were really with, so the question might be like, is, wow, let's try that again. Is nums I a duplicate or a new value? That's sort of the question we want to ask in this code. And so how do we play that? I is the next element. Oh, all right, but this is not. I'd write if nums equal to 1. So I'll make sure we know what this word means. I guess we have dead air, which we shouldn't have on TV. So this is it.
So, yeah, we're checking to see if -1.
Yeah, I think
1, but okay. So that's it.
That's an I on the 1.
What's the one time this? Just
I was going to ask you.
I'm guessing open.
You're guessing on then what can we? There's a reasonable guess, but like how might we be more confident?
Open.
Because I get more confident.
Because it's an array and we're iterating the way, so we never know the size of the array could be bigger or smaller.
All right, so this is just sort of the end of the length of our array. This for loop happens n times, and the way to really make sure is like, okay, this I is never changing, like it only is getting here. And how long does each iteration take?
Constant time.
Yeah, so here's it. Or here's some arithmetic. Or and that's it. That's the loop. Otherwise, it just has.
I have always been confused when
So yes, it is over. Just sorry, yes.
I've always been confused by adding to the camera there in the
Yeah, sorry. I should not do that. That's okay. Like, it's a fun trick to know, but I think there are more important things to be comfortable with first.
What you just did, and you're saying that C gets evaluated first.
Yeah.
And then it gets added after.
So this is a, I won't say this is like super duper common, but when you had actually previously talked about how that there's that other question of like having an array of stacks and so on. Another way of conceptualizing this question is saying we're now actually going to have, so of course there's only one array in memory, but we're going to have two arrays. And they both overlap. They both start at 0. And this is the pointer, this is the index of the element right after the unique array. So this is saying, alright. So this is saying, here's the next, if we're going to add an element, this is to our unique array. This is the index we'll add it to. So implicitly, we've already added the 0 index. That's what I was saying. Like that's what I was saying. Okay, of course, the 0th element is unique in the sense that we haven't seen anything. So the next space we have to store the unique element is in the index 1. So this is sort of the next place we want to store the next element we've seen. So really, we're copying sort of the original array back into the beginning of the first array.
So it's like having two pointers in a linked list kind of. We have, I is referencing an index, and C is another one. With what that allows us is kind of think as if we had two arrays, or kind of overlapping.
Yeah, actually doing this instead of an array with a linked list would be fun as well. It won't look too, obviously the syntax will be conceptually similar. That really, and so this pattern, so we were talking about before about how removing an array, an element at the end of the array, is sort of just decrementing its length by 1, in a sense. Or we can implement removal. Here's sort of its counterpart, where we're saying, to add something to an array where we know we have more room, we can just increment our length by 1. We can say, here's the end, but we know it's a valid. So there's a lot of machinery going on. We know there's still extra room. Like this isn't going to be an array out of bounds error. I guess it just kind of trust me on that. I don't mind quickly somewhere. But it's pointing to the next spot. So here's sort of, if you mention a very big array, and we're doing this operation, and it has a lot of repeated elements, we have, here's the array, and I might be ultimately pointing here. There's still this function process. And meanwhile, we've been building up a unique array here. C is pointing. I think I'm just going to end up repeating myself at this point, like lots. But yeah, I mean, the idea of C is kind of pointing to the next thing, I add this little one of that we're applying. And that's also why we do minus 1 here, because we're saying, what's the last thing we actually add? If this is the index we're going to add. Or units.
Yeah, I think that visualization
Oh,
here for me.
okay. Good. Actually, that feedback to that. Oh, so I mean, genuinely, do we believe this? Because there's sort of a lot of fun little pointer arithmetic going on here. Let's see.
This works.
And again, I encourage you guys to go through the link directly. And that's also why we're sure C. So nice and neat. C is exactly the like this is the one extra button. I'm going to erase this. Yes. So I'm glad I spent a lot of time at least trying to explain that why we had C be the value of class. And also I just want to think that. That was really cool that you guys seem to pretty much get the outline of the right approach. That's a bit of discussion. I want to encourage you again, you know, getting the right outline first step and then driving it home with actual code is harder. Rather than like, you know, in the sense of like, okay, then it's a different exercise of getting all the details right. That you can do with the auto graders on these websites and go for it. Yeah, this obviously I don't, for now, obviously, but I usually do it in C++ on these things. And this didn't print correctly, so I need to print it up. But like, the operator seems accurate. And I'm always around finding someone was like, oh, I have a question at one side. I was like, hooray, and they were like, it's about, it has nothing to do with data structure knowledge. All right, so, but seriously, always feel free to ping me and sorry for using a computer. Okay. Okay, good. So, here's the question. So, all right, we're done with the first one. We're moving on to a 3 equal partition array thing. This function, it returns a bool, true or false. And it's food. It's a long name. And it takes an array, again, you know, int array. And what it's asking, and here's a big example. We could have an array of integers and they're not sorted. I mean, they could be sorted, but not necessarily. And they could be positive, they could be negative, they could be 0. So we're pretty open-ended here. And what it's asking is, can we so here's some vocab. Partition. If I ask you to partition an array or a set, does that ring any bells? Have you heard that before? I'm sorry. Oh, if I say here's an array and let's partition it, okay, that's a bit of a vague request, but like, have you heard the word partition before? Is there any context?
But what are we partitioning by sorted numbers?
Okay, yeah, so that's why I was saying it's ambiguous. I'll explain how we want to partition it in a second. But so, sort of a name, like we want to cut it into parts. Right? And so if I say we want to partition it into 3 pieces, we're still oriented. That's still not the full answer, but like, okay, as opposed to 2 pieces or whatever. So what we want to do is we want to partition this, you know, our input array. Here's one example. Into 3 non-empty parts with equal sums. Equal sum. Yeah. So 3, we got that. Or you know partition, we know 3. Non-empty. So we'll touch on that. And then equal sums. That's implicit, but probably, hopefully, intuitive, just still on the website.
Okay, partition into 3.
Yeah, so I'll do it explicitly. So I'm just rewriting here. 0, 2, 1, -6. So I'm just making up the syntax, but you know, maybe we would have a partition here. 6, -7, 9, and 1. And maybe another partition here, and 2, 0, 1. So I mean, I just drew big lines in partition. But so you agree that this looks like, okay, we partitioned it into 3 pieces. And just actually for explicit, if the partition were here, this is invalid. And why is this invalid? According to
The partition, the second partition sum is not equal to the first partition.
That's fair. So actually, I just mean forgetting either whether we want to consider possible partitions. We want to consider partitioning into 3 things that are non-empty. So I just wanted to exercise the idea that if we put our partition here, you know, this part is empty. So when we mean by, it's pretty intuitive, I think it's sort of funny phrasing. But like non-empty means like, okay, every partition has to have something in it. So this partition, for instance, or this partitioning, each partition is not empty, simply, and by that, it's not that, oh, it doesn't sum to 0, it's that it has at least a number. So,
but now the sums aren't added up.
Okay, so
The sums are
you guys are ahead of me. So what's the sum of this partition?
three.
3.
Negative 3.
Yeah. Okay. What about this one?
2, 7, 9, positive 1.
That's 2, 3, 9. And then 3. So for this, with this part, I'm not saying we should return anything because there's a lot of different partitions we can try, right? But this partition is not what we're looking for, right? I'm just making sure we're on the page. But let's say, I guess that's the word. What would change here? So this doesn't change, right? Just like we're jumping ahead, but like, okay, we didn't change this partition, this still sums up to 3. Now we have removed, we've included the new number, which is negative, so we'll subtract it from this. And what's this? So now we've taken away the number -6, so we should add 6 to this. You get 3. Ooh, that's nice, right? So on this input, in a way you can say, okay, this partition is sort of a certificate. We're not returning 3 or anything, we're just returning true or false. But in the way that we can honestly implement this algorithm is we have to find some partition that has this quality, so we return true. So that's what we want to do.
So, and we have to link this not just for this array, but for any array that comes up.
Yeah, that's sort of getting at the heart of the idea of the algorithm. Not just this solution, or not just this input, but like what's the way of finding a solution for any?
Just the pseudocode, just off the top of the head, I would say we need to iterate through the array. But what input are we taking to understand what number we're looking for?
So yes, that's how do we know what the value of the partition should be for?
Yeah.
In this case, yeah, I don't know how to. I want to always provide you a handle for future questions. In this case, we're just looking for equal sums. So we don't care. We just want to find any grouping where they all end up equal. And so in fact, for instance, I forgot again, motivation for this question. I actually had to do something sort of like that. But I wanted to solve this problem very similar to this. Because I wanted to check in some code, and we needed to run and I needed to run a lot of tests. The tests would take a long time, like many hours. But I was given special permission to access, so my friend said yes, you can use these like 5 very powerful computers to run the tests. So I had 80 tests, but they ran at very different. Some took 1 minute, some took 20 minutes, some took 4 hours. So I wanted to partition them in a way where they would be most evenly, intuitively, right? Let's divide up the work so they all, take roughly the same amount of time with the intuition that I remove the total amount of time after. So it doesn't need, in that sense, I don't need to know like, oh, they will all take 3 hours or 4 hours. I just want them to all have the same amount. That was a slightly different problem because we're not changing the array order here. I don't want to confuse with that. Here we're stuck with this array. And we also have regular but I guess that was a very good question of, well, what's the number we actually want to solve? Or we want to partition it over, but kind of from this question, it's actually not, we don't have to worry about it. Is the optimistic way of phrasing it.
That for me, it makes it harder for me to solve. So what I would want to do is add up the sum of the total values of the array, get that value, and then being that we're looking for 3, take whatever that value is divided by 3, and then look for it in the array again. But that just makes it, I'm already at 4 n squared if I do it that way, and that's just super cool.
Oh, well, so for any sort of question, especially one that seems sort of like a lot of branches to explore, don't worry about performance or efficiency. Let's actually, so I definitely see the intuition of your intuition, oh, let's add up the numbers and divide it by 3. I'm concerned about how negative numbers would interact.
Yeah, that's true.
And if I were just, well, we could say, okay, this
We only
is,
have 2 of them.
yeah, well,
Like,
like, so this is 0, this is 3, this is 3. This is, oh, well, it works out there. That's nice. I'm not like disagreeing, but I'm not sure if finding,
yeah, you want to make sure, but
well, obviously I didn't find this one. But,
I'm thinking that we'll, since we have a restriction that we can only partition into 3 parts, I'm thinking we'll need to partition this array into all the, or I'm not sure what the right word would be. Like extract all the, partition this array into 3 in all possible ways.
yes, so I don't know why I'm popping in at all now. But I like what, sorry, do you have more to say?
No, I would like you to editorialize it.
Okay. I know. I hope that's a good word. I don't know if that's the right word to say. But yes, so your intuition is saying, okay, what we can do is trial the partition. I think people use the word interchangeable, like partitioning, partition. But we could, so we could say, all right, here's one partition. In one partition of 3 parts. Dot, blah, and blah. And then we can do blah, blah, blah. And then we can do something like, blah, blah, and so on.
That will be like brute force get all the 3 partitions.
Yeah, and that's cool by me. So how might we, so forgetting even the actual goal of finding which ones are equal, how might we kind of explore all possible partitions?
Wait, did you repeat that?
Like, so forgetting that we want to find the equal sums and stuff, just like how might we sort of have a loop,
Like,
or some way of looping over?
like actually building the partitions, or like,
Yeah, sure.
I think maybe we could do everything with pointers or the indices. Keep track of where the first partition starts and where it ends, and where the next one, the next one will start where the previous one ended. And then the last one will start where the prior development ended.
Yes.
Yeah.
So we're thinking, all right, we want to just find all partitions, and the question of how do we express partitions? So all under this idea of, well, we can basically just keep an index of saying, well, here's where the first partition ends, for instance, and then maybe another index of here's where the second partition ends. We can exploit the fact that the second partition has to start where the first one ended, just because that's how the problem goes. And then implicitly, the third partition ends the end. And begins where the second one ends. So that's how we might represent our partitions. And I think that's very neat in a way, and I've always had shown this this is all sort of implicit. Like, the one hand partitions is like, here's this, we might want to make separate sets or separate array lists or whatever. But we don't need to, and I promise we don't need to do this question. Here we can just sort of implicitly say, well, this range of pointers, or range of indices, from the beginning, this one, from this one to this, and so on, they represent our partitions. And that helps make a lot of things work, and in this case, it'll help us be very efficient. I know I was saying let's not worry about efficiency yet, but just sort of like, also in a conceptual sense. And then implementing it system. So, in other words, we might be able to represent 3 partitions as just 2 numbers, right?
The end of the first one?
Yeah.
The end of the second one?
Yeah. So, how might I'm going to repeat this question, I guess. With that, I think we've taken a few neat steps. How might we is there a way of kind of iterating over all 3 partitions? How might we?
Iterating over all 3 partitions. Like just taking note that we have in we have where the first partition ends and where the second partition ends. So we could loop and just taking into account taking note of when we see these partition points, so that we can try to reset maybe our sum. If we were summing, reset the sum. No, we need to keep track of 3 sums.
Yeah, oh, so that obviously will come up. Now let's just try to explore all the partitions. We're not even trying to sum it.
Okay.
So a very general technique that's so general it's kind of hard to think about sometimes is, let's just simplify it. Forget answering this problem. Let's answer it simple. So imagine if there were 2 partitions. By which I mean, like, let's just worry about 1 partition. Or, you know what I mean, 1 line. The way of exploring, or
Wait, we're partitioning the whole array or just, are we moving the partition along?
sorry, what was the second word? I just,
Or are we moving the partition along?
yeah, sorry, I mean, partition is an overloaded, I'm using it in an overloaded way. Where I could either, like, this line might represent a partition, like, this is the thing cutting. But then also, I would use the word partition to mean this part and this part. So in a sort of confusing way, this partition defines this partition and this partition. Sorry, it's overloaded. But what I mean is that, like, you know, the way I was drawing it before when you were talking about the answer for this input, like this line represents this, you know, these 2 lines define these 3 chunks, these 3 partitions. And so now I'm saying, well, how might we kind of explore all possible ways of chunking this array using these partitions, using these lines? Remember, if you know, that's sort of complicated. So a simpler way of approaching it, or like a way to get a handle on it, maybe say, well, let's forget 2 partitions, and let's just talk about chunking the array like this, and to see how might we implement this way of exploring the partitions. Just simplifying it.
So I think now I see, we will, I guess like the word is kind of throwing me on this explore.
Oh, I'm trying to be very vague, so I guess I'm saying too much.
It's because I think like, well, if you want to kind of build or take note of all the possible partitions, we could just move the partition line by 1 index every time. And by the end, we will be sure to have all the possible partitions, all the ways in which we can partition this array into 2 parts.
Yes. So I like what you're saying, that's sort of what I was right here. And so for instance, I'm really making up syntax here, but this is, I hope that will clarify what my very vague explore word. So obviously it's not yet what we want. This is if we're partitioning things into 2 chunks instead of 3. But yeah, so it's kind of following through with all the idea of using just a single integer to represent where we divide our array, where we partition our array. We can do this, which is we can partition at index 1, and then we can print out, hey, partition 1 is the elements 0 to 1 of A. And then we'll print out just this. So it's all elements up until, but not including I, because that's just, you know what I meant.
And that,
Less than I.
at some point there, you're increasing J.
Yeah, sorry.
But,
That's what I get for being
but
quick.
I think it's fine.
Well, J is there. J is less than I. J plus. Then J equals I. J is less than A plus A plus B. Yes. So this loop, when I is 1, will print out just 0. Or sorry, this loop, when I is 1, it'll first print out 0 for partition 1, and for partition 2, it'll print out J from 1 all the way to the end. And that, like, we're just printing it here, but that's what I sort of mean by, like, hey, when we're in this loop body, we know what this, we are looking at kind of the next, you know, each 2 partitions of the array. So that's a neat idea that I hope we all have internalized. So in the interest of time, I can go a little faster. I guess it's hard to say no now. So, sorry, I'm erasing this so far, so good. Okay. It's not being here suspicious. And then building off the idea that, okay, we don't want, so I starts at 1 here, because we know we don't want to worry about empty partition. If I started at 0, then the first partition wouldn't have it. That's just maybe the correct question. A natural question. But we don't care about partitioning into 2 pieces. We want to partition it into 3 pieces. And one way we can think about it is saying, okay, this is basically telling us how big our first partition is. The first iteration, first partition will be here. The second iteration, our first partition will be this. The third iteration, our first partition will be this. Oh, like that's always going to be true, whether we care about 2 partitions, 3 partitions, 4 partitions. So for every single partition, first partition we choose, so this one, how many different ways can we have the second partition look like? The second and third partitions. Yeah, it's hard to frame. Sorry. But as in, okay, now we want to have not just 1 partition, but we want to have 2. And so from a human's perspective, we can say, all right, if we have now fixed our first partition to be here, then we can either have our next partition line be here, or it can be here, or it can be here.
I feel there's a math language that will express this really well, but I don't know. Would it be like I mean, it has to be
Well, maybe put me on the spot. I mean, so partition usually is used in a sense where we, hold on, I don't have videos like that either. I want to say that partitions usually are in a sense where we don't care about the order. This is a little unusual. Here, so just to get to the punchline, I would write this. That's saying for int j equals I plus 1. And I say plus 1 for the exact same reason that I start at 1. Because basically between I and j is going to be the middle partition. J is less than A, it's not the size. Semicolons. And so then here, in this loop body, between 0 and I, then between I and j, between j and the n, those are our three partitions. And to your question, okay, what's the nice mathy way of talking about this? Roughly, I always get these off by 1 error. When you have a loop where it's I, and then the second, like I is on normal, and then j, which starts from I, starts from I plus 1. You can imagine it like, keep it analogy. Well, if you had i's from 1 to 8 outside and j from 1 to 8 outside, that's sort of like a square, right? I, then you have, does that make sense at all?
I was thinking about like the formula where you add up the numbers 1 to n.
Yes.
Actual numbers 1 to n, but then I think there's a multiplication factor. But
Yeah, well, so I agree with you that we'll basically have, in terms of how many times this body will iterate, it'll be roughly n choose 2, which is roughly 1 plus 2 plus 3 plus 4, which is roughly n squared. What I was trying to say is, this is, if I is 1 and j starts at 1 as well, but if I starts at 1 and j starts at 1 and 2, there's something very angry. That's just sort of, again, these are all different webs, that connect different concepts and ideas. Beautiful web of mathematics. But visually, going back to this very tortured example, if you kind of draw this out, and I would encourage, so here's the secret, right? I've been doing this there's people who are doing it a lot longer than me, but I've been doing this for a while. And every time I sit down with these questions, these online questions, I have a pen and paper, or pencil, whatever. I have a human writing instrument. I don't just always type. And I literally drew like line. And I started seeing like, oh, hey, here's all the different ways of partitioning it. And that's where these things came from. So I just want again, I have a lot of context to build off of vocabulary. But really just kind of drawing examples. Like, once I said, oh yeah, if these are not empty, then I have to leave space in between. It's just all a little, helps me avoid a lot of problems. That's sort of a general tangent. So, do we believe that we haven't even done this sum yet? But how can we print out? So, can we use these two loops to print out every possible 3 partition of our array? The answer is yes. And this is to help drive home the idea of we really can represent the 3 partitions with just these 2 integers. So if I have,
You can use a sub.
sorry?
I was thinking about a sub string, but this isn't where you can use it.
So we can't use that method, but there's definitely that idea. So in fact, we can say print, and a common word is not used in C++ so much, but I know other languages slices. So if we have print slice A 0 I, print, so of course we have to implement a slice, I, j, and then print slice A, j, a dot size. Okay, I should have opened with this, sorry. There we have void, print slice, here A, beginning and end. So sorry, I'm leaving out types now. Before, nothing, E less than E, B plus plus. With A sub B, I guess.
I don't think we have that in Java.
Oh, slice?
Slicing a string, yeah, but you guys have it in JavaScript.
Try not to be jealous there.
I guess I was getting confused because I was thinking, oh, for representing or exploring the third partition, we will need another loop. And in fact, we do have another loop.
Yeah, so that's a good point. Print slice goes over a slice of the array. So I just want to make sure we're all on the same page. But print slice here kind of prints out the first partition. And then here prints out the second partition, and here prints out the third. This is sort of like a big deal, so I want to spend a bit of time on that. Like, oh, this is, and there's a lot of variation where it's like, oh, we have just an array with a little bit of extra information, ij, a lot of imagination. We can imagine, oh, hey, we've actually created this partition. And we can interact with the data as if it's partitioned in this way. Even though we haven't explicitly built like a set, 3 different sets in there. I have notes that one day I want to present on the heap data structure and heap storage. This is just a tangent, but where you use an array, again, kind of with that imagination, you kind of define a tree over that array. So kind of in the exact same way where it's sort of like, there's no pointers, there's no parent node or left child node or anything. But kind of again, by putting more interpretation over the instruction, you get something out of it. And so this is believe it or not, this is a simpler thing that you sort. But you'll like to see this, how like, oh, hey, here are the few things. Yeah, okay. Go on. Wait, we haven't solved the question. So if we have these 2 partitions, and like, this is all possible free partitions of the array, can we solve our question now? Of our actual goal of finding if there is such a 2 partitioning where all 3 of them are equal? Yes. Alright, so I'm right.
Yeah. I think instead of printing, we could just add. And then we can see if the 3 sums are all equal, in which case we return true. So how do we return false?
Also, I want to make sure before we get there. No, I was going to ask, because you said are we adding up the partitions and what they contain, or are we adding them individually?
We're adding the elements of each individual partition. We get the sum of that, and we compare it with the sum of the next partition and the next one. At some point, we will either find the answer or not.
Yeah. All right. So yeah, your question is just, it's good to make sure we provide what our customer is asking us to implement. So yeah, like it's just as here's the sort of slice, the subarray from 0 to I. It's like we want to sum that, and we also want, and then that's its own value. So I won't actually implement it. It won't look too different from this, but you can imagine we have a helper function, the sum slice. So we want to sum. Is that us? Or is that us? No. Oh man. Oh, then you're good.
Well, then you went on.
You're a very good person. I didn't realize that was I thought it was someone I'm talking. Suppose you can also do it. That's not very good spirit. But yeah, so I agree with your intuition that we can some of these slices look at their input, and then you were asking also, you raised the question of when do we ever return false, or how do we return false? it seems that you were getting there.
So I guess like the easy way that I was thinking is just inside of.
Sorry,
I was thinking about like just return some slice of the first partition equal to the second partition and equal to the third partition, then return true. And otherwise, so if we went through all of them, yeah, that's
if x equals y and y equals z, return true.
Then once we exit out of, once we're done with the loops and we never run into this return true statement because if it happened, then it would return false.
Yeah. And that's another, I wouldn't say super duper common pattern, but that idea of like, okay, we want to know if there exists a partitioning of this array. And we have this is a nested loop, but we have a loop that searches for every possible partitioning, and if we don't get it, or so yes, you're a good person. So yeah, how does this flow of this work? There's a somewhat general pattern. It's like not like a programming pattern, but okay, we want to search through every possible partition, and if we find the thing we're looking for, so if we find that, oh, hey, these three sums are all equal, we return true. When do we return false? Well, it's when we're done, we iterate through every possible partitioning you can think of that exists. If we get to the end, then we return false. And that comes up fairly often, usually like just kind of one array. And it's like, does this array have the number 4 in it? Yeah, well, you go through it. If you find 4, you return true. And if you get to the end of the array without finding it, you return false. And so here, there's that implicit thing of like all possible partitions. So here we're iterating through all possible partitions, and we find a new one for return the false return. So hooray, this works. And what is its runtime?
It's no less than quadratic time.
All right, so comment. Not that people are going crazy, but all right, let's one thing at a time. How can we break that down? How do we?
Well, we have super loops, right?
Yeah, so that's super loops. What's the first loop looking like?
Constant. I mean, not constant, or then.
Okay, yeah, so here, we're going through, sure, this starts at 1, but 8 doesn't matter. Or then.
And then or then for the second one.
Right, so I'm going to poke a little bit and say, well, hold on, it's starting at I. Surely this is a little faster, right?
So or then -1.
So, all right, so sorry. I don't do this anymore, but I try to mix it up around. So I agree it's a little bit, this is okay. And if someone says, some bully on your code review saying, I don't think it's open, convince you.
I had the feeling that I would start from the inside out.
Okay, so you want to approach
I don't think that will make a difference.
Or no, sorry, in terms of we can say, well, this loop iterates O(n) times. And Janelle's saying this loop also iterates O(n) times. And I'm going to be a bully and I'm going to say, no, I disagree with you, convince me.
I know that there is also a math formula that expresses this. But
That's why I thought the whole of n -1, because that's the only thing I can see is -1 from whatever I'm doing.
Well, the magic of O(n) or big O notation, roughly speaking, is that you don't have to worry about constant. So what I'd say is look, I starts out as 1, so J starts out at 2. A is really big. It doesn't really matter. It's just going through, if n is 1,000,000, okay, you're iterating 9,900. So this is still, at least the first iteration is still basically n times.
I see.
And then this is actually that sum you were saying. It's really going to be, that's like, n minus 1 plus n minus 2 plus blah, 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 plus 1. You turn that around, you get 1 plus 2 plus 3. All right, it's all a little pain. But this is all just to say that, hey, we can, O of n is the worst, or big O equation is the worst case. The worst case is that this is basically the whole length of A. If A is huge, it doesn't really matter which A is with 2 cells.
Yeah, I feel like for
Not super contemporary, but the code reviewer is building so way.
I feel like the math argument does, like, I have seen in Crockett interview how they derive of n, like, by removing the constant at some point. And like, at least for me, that did make it like,
Yeah, I encourage you, of course, to look at, the stronger you can make your arguments, the better. For brevity and arrogance, for now, I'm just going to say, whatever, it's O of n. So we have O of n times O of n. So how many times does this body of the nested for loops happen? Right, if the for loop, if an O of n loop is nested inside of another O of n loop, which shorthand?
all things squared.
Yeah, is that surprising? No.
What the shorthand?
Or well, just that, like, oh, okay, because this is nested in here, this body, we can say, all right, it'll iterate around O of n squared times altogether. So I'm sort of combining these nested stuff, saying this will iterate O of n squared times. So what I'm doing is, like, to kind of understand the runtime of this algorithm. I'm saying, all right, we know this is O of n. This is O of n. All right, so like now I can sort of throw those away. And just what's left? It's the run. Oh no, is it rain?
Yeah,
Fun.
I think
How long does a single loop on there? You know what I mean?
Yeah.
How long does this work take?
I think it's gonna take O of n. Because your x is gonna take a third of n, and then y is a third of n, or roughly. I guess like what I'm trying to say is that in total we'll have gone through the array once. So
Yes.
yeah, I'm not sure how the wording is correct, but
Yeah. I mean, a third is here. Well, when I is 1 and j is 2, it won't be third.
yeah.
But yeah, so riffing off, assuming some slice looks like print slice, and it does. Okay, like here we're iterating through the first chunk, and then the next chunk, and then the final chunk. So we're sort of touching an argument to say, like, look, we touch every element of A once. And the first chunk here, the second and the third last here. So to go over all of A is O of n, because we're saying A is like that. So altogether, this algorithm that we've written is cubic. Roughly speaking. Cubic is bad.
Yeah.
Okay.
Are there ways to improve this?
Yeah, so I said, oh great, I solved this question. I hit the submit button, they said, your code is too slow. Oh man, all right, fair enough. And actually, I've been thinking also, I think you're interested, Darnell, though we can just add them and divide them into thirds to get the number of what a partition would be. I think that's right. But don't like completely quote me on that. That would be worth exploring. I just wanted to get that up on video.
That would be like getting the average that you get. Or
No, what I was thinking, yeah,
Well, that's not just, sorry, that was just a table.
you know that we want to divide it into 3 parts. So what I was thinking was no matter what is in the array, we add that up and divide by 3. So that way we know, then we'll take the length of the array and divide it by that same number to get the partition. So the way you would get the middle of an array is you take the size of the array and divide it by 2, and then whatever it lands at, that's the middle of it. So that's how I would get the partitions.
Yes.
Yeah, sorry, I wasn't catching it. So yes, in terms of making it faster, all right. No. So we've identified and we've convinced ourselves in our code review that this is a cubic algorithm. Yes. And I think we touched on, oh, sorry.
I guess I'm just thinking that we're gonna, as very often we do, sacrifice some space in order to gain some time. Or does it trade off most of the time? So I'm kind of, that just came to mind.
No. So you're thinking, okay, maybe we can save something.
Yeah, that was thinking, but
Yeah, well, it's all right.
we're trying.
I'm getting a little tired. Give me a second.
No, it's okay.
Ha. Yes. Alright. Yeah, so there's this idea of, or if we think about this, like, imagine how it's going in our head. That's what I was trying to get at with the slot count. Like, when it's like, okay, we seem to be kind of doing a lot of the same additions over and over again. If, for instance, we're looking at a addition here, and so this is, I is 2, J is 6, and then let's say we update, and we've summed this range, we've summed this range, we've summed this range, and then we increment J by 1. Well, then what do? We end up here, and we sum this, and we sum this, and we sum this. And it's like, hold on, we've added these pairs a lot of times together. We've added, this chunk itself a lot of times. Like, maybe there's something we can do there. And I think one of you guys mentioned at the beginning, well, we can sort of keep a variable, like, oh, this is the current sum. This is a loud share. And we have 5 minutes to roll. But there is this intuition of like, well, yeah, time flies, we're having fun. Oh, yeah, this was a 1. But like, okay, kind of halfway through our algorithm, if we have like, this partition, and we oh no, that's the answer. Or, no, not quite. But so here's 3, and imagine there are different numbers for that. But so this is x, right? Like x is 3, and then y is 2, and z is 4. And then if we want to look at the next partition, we really, we're just moving this number from this chunk to this chunk. So as we've written this, when we move, this line from here to here,
Just subtracting.
yeah, well, yes, so currently we're saying, all right, we better sum this up again, sum this up again, sum this up again. But I was like, we've sort of already done this sum. But we can, as we were saying, we can just add the new value to this and subtract, but whether it's positive or negative, we add that number here because we're adding the partition, then we subtract from the one we're taking away. So now there's some intuition that, hey, this is reduced to just a few, like a constant number of arithmetic operations. And in fact, if you like, we can observe that, hey, wait a second, that's just for fun. That doesn't, obviously, maybe that's a topic about it. That's a quick and easy way to do it. But no, so we're not going to go through it probably for I implemented something hacker that actually sort of exploits terminals idea that I was skipping over. But yeah, so I encourage you to try this, get the most efficient thing.
Thank you.
Yes, I'm sorry, I'm very clearly late, so stop here.
Yeah.
The last thing I do want to say is, there's a very, very, very exotic data structure. I'm not encouraging you to like look at it, just so you go with this called a prefix tree.
Oh, I've seen it.
Oh, well, all right, why? I just said it's super exotic.
I'm studying that.
Okay, well, good, all right. So, yeah, then you should run it up. But as
I'm an expert in it. I don't understand it.
fair enough, but it captures the idea, it succinctly expresses the sum of this subarray, and then this subarray, and this subarray, and this subarray. Which is not the answer we're looking for, obviously. Like a prefix sums, sorry, I'm gonna erase this. It's on video, so whatever. So a prefix array would be 0, 2, 3, -3. What it is this is the sum of this is the sum of this is the sum of this subarray. So it's each, the idea. If someone says there's a super duper efficient algorithm for solving this, I bet it would involve something like this. I have no idea how, they didn't say, but that's just, structure of imagination. It came to me on the train, and I was like, I know we could do something really cool with this. I also could be wrong, I'm not promising anything. But either way, the thing we outlined before, like, we can just shift constant each time. Yes.
The other structure. Have you read, I don't look at it.
All right, I think, sorry, should we end the episode here? Some cliffhanger next time. Thank you guys for shopping. Thank you for watching. The millions of viewers at home.